Chapter 4, Chemical Foundations. Up to now, chapters 1, 2, and 3, we've gotten information that is applicable to any of the sciences. Now we're going to start dipping our toes into the chemistry pond. And for the exam 2, we cover chapters 4 and 5 only, I believe. Yes, chapters 4 and 5. Before I get into this, you will find PowerPoints in Brightspace. You'll find a review document for chapter 4 and 5. You'll find a key in the module, be module 2. You'll find worked problems that'll tell you how I worked the problems for that review document. And then you'll also find 2 extra credit assignments. These are voluntary, right? You don't have to take them. I just thought that they would help you master the material. And one of them looks like this. I probably already showed this one to you. This is the periodic table. You just follow the instructions, complete the table, and either turn it in person or photograph and submit it in Brightspace. If you would, include the top cover, because I use the top cover to grade, go by the points here, and your name is there too. You might be, well, maybe you wouldn't be surprised how many students forget to put their name on their work. And then this one is naming your compounds. We'll get to that, I believe, in chapter 5. And you just fill out, this one you only need to turn in this part of it with your name on it. You either give the names of the compounds or you write the formula for the compound that is associated with the names. Like I said, these are extra credit, but I think they'll help you. If you can do these, then you'll be one step closer to mastering the material. Okay, now back to chapter 4. Chemical foundations. Where do we start? We start with the elements. Right? The elements are the building blocks of matter. I used to say there were 115 known elements. There are actually 118 now. And rather than swivel the camera, I'll just point over here, and there's a periodic table on the wall. And every place in that periodic table now has an element with a name in it. There were placeholders previously, several of them. And they were the heavier elements that are man-made, actually. But the International Union of Pure and Applied Chemists finally came up with names for each of the elements. And there are now 118 of them. Approximately 88 are found in nature. It's probably higher than that because our analytical techniques become more refined. They're able to detect smaller amounts in nature. So some of the previously man-made elements now we can find in nature. Not all of them, but a few. Another estimate is 98 rather than 88 are found in nature. Okay. The elements are the building blocks of matter, and our job is to give them names. Give them names where we can't write out the elements of the compounds that they form using their complete names. I mean, that'd just be a mess. So we have a system of symbols that are associated with each of the elements. And they're based upon either single letters, which are always capitalized, such as hydrogen. Okay? Or if that letter is already taken and we need an H for the symbol, then we add a small letter behind it. For helium, we would say like that. And it's always just two letters or one letter. One letter capitalized, two letters capital small. Always that way. If you write this for helium, it's wrong, and it will be counted wrong. And the periodic table that I distributed at the very beginning, I think, looks like this, just like that. Has all the element symbols, doesn't have the names, only has the symbols. So you have to look up the names. And the ones I want you to memorize have red boxes around them. So you have approximately half of them, 60 or so elements. I want you to know the symbols for these. All right, so you make flashcards, put the symbol on one side and the name on the other, and just drill them until they're drilled into your head. That's really the only way to memorize them. That's a good way to memorize them, is to make the flashcards yourself. Because when you make the flashcards, you're starting the memory process. And then you just drill. You have two stacks. You have got that one right, got that one wrong. Right, wrong, right, wrong, right, wrong. Then you go back to the wrong ones, work on those until you finally get everything into the right pile. Then you go back and do it again. When you can go through that stack of cards with the element names, the symbols on them, both directions. In other words, look at the names first and say the symbols. Check it, put it in the right pile. If you can do that for every one of them, then go back, take the symbols, have them arranged so that you're looking at the symbols first, then name them. Get that one right, put it in the right pile. Do that. So if you can go through either way, symbol or name first, and get them all in the right pile, then you're in good shape. Okay, and this is that same periodic table that I showed you before. I couldn't find one like this on the internet that I could reproduce. So I just said, I'm wasting my time. I'll build my own table. So that's the result. And as we proceed through the semester, the structure of this table will become more evident and useful. Right now, it just looks like a jumble of letters and numbers, but it's arranged this way for a reason. And once you know how it's arranged, why it's arranged that way, you can extract a lot of information from that one table. Okay, so the elements, they're not all equally abundant, right? There's some elements that are a massive majority in the universe, and even in the crust of the earth. In this case, we're talking about the distribution of these 18 most abundant elements in the Earth's crust, oceans, and atmosphere. So we're not talking about the mantle or the core of the Earth, just the crust and up. So the crust, the oceans, and the atmosphere. These are the percentages by mass. So the highest percentage by mass is oxygen. And that really makes sense. Because for one thing, the atmosphere is 21% oxygen. 20% oxygen, excuse me. And the oceans are H2O mostly, right? So you got oxygen in the oceans. So it should not be a surprise that almost half by mass of all the elements in the Earth's crust, oceans, atmosphere is oxygen. The next most abundant is silicon. And that's primarily due to its presence in the crust of the Earth. There's a lot of silicon in the earth. Walk on any beach, right? Squish the sand between your toes, you're walking on silicon dioxide. So silicon is very abundant. Aluminum is very abundant. In fact, well, my PhD is in soils, and we know about the structure of soils. In fact, at the atomic level, aluminum, silicon, aluminum, iron are extremely abundant in the soils, and the soils are derived from the rocks underneath them. So the crust of the earth has these major components. Well, now I'm talking about the crust. Oxygen, silicon, aluminum, iron, those are extremely abundant in the Earth's crust. And then you have lesser and lesser and lesser amounts of each one. Hydrogen's not really that abundant by mass, right? Even though there's lots of hydrogen in the ocean because it's combined with oxygen to make water, but by mass, it's a very light element. It's the lightest element. So by mass, it's not a very high percentage. Okay, we have these others that are lesser and lesser and lesser. Notice carbon, the stuff that makes us possible and living things possible, is a very small percentage by mass. Okay, so there must be something else at work. If these, we know these are very important elements, extremely important. So there must be something more at work here rather than mass. And we're going to talk about that eventually in terms of numbers of atoms, because that's the way they combine to make things, not by mass, but by numbers. Okay. All right, I mentioned this earlier. The AR, for instance, is argon. Let's see, why don't we use A? There's no element in the periodic table with just A, but there are lots of words in everybody's language, at least the ones that are based upon the Latin alphabet. So it'd be kind of messy to try to identify an element just like this in a sentence. You wouldn't know if it was the article or the element. And so we kind of, there are practical reasons for not using some of the letters to represent elements. Instead, we go to AR for argon. Okay, we go to AL for aluminum, for instance. Hydrogen, yeah, that was sort of grandfathered in. Hydrogen was well known by alchemists. Now, this system that we're going to use, where we have individual letters or large capital letter and small letter to represent an element, didn't just come to us out of the heavens, right? We had to figure it out. We had to agree upon it. And there were competing proposed ways of representing elements, and the rest of them were just unwieldy. Maybe we might call them garbage. They were pretty much useless. I mean, they were pets of the scientists proposing them, but they weren't very useful. Eventually, we settled upon this system, and it was proposed by a Swedish physicist, chemist, Berzelius. And I'm kind of glad that he won out. It makes a whole lot more sense this way. Okay. Now, when we talk about an element, we actually needed a definition, right? Did we define this in an earlier chapter, what an element is? I don't think we did. I'm I get my other courses conflated. So I have to back up and say, have I introduced this topic yet? Okay, so we need to define what an element is. An element is a unique substance which cannot be broken down any further by physical or chemical means. In other words, it is the simplest form of matter in the chemical universe. Right? When we start getting into nuclear physics, yeah, you can break an atom apart, and we're going to talk about that in a minute. But for chemical purposes, the element is the simplest form of matter. In other words, if you have more than one element combined, and you try to break it apart, you can do physical means. You can separate things first into smaller amounts. But then when you start using chemical separations, you can pull those elements apart. And eventually you get to where you have something that's pure. And it only has the characteristics of a particular element and none other in it. So oxygen's an element, hydrogen's an element, which may have come from water. Didn't have to be, but it could. Break the water apart. Now you've got elements, oxygen and hydrogen. You can't break oxygen apart any further and make two or more different elements. That's it. They have characteristics that are unique to that element. And we're going to talk about what makes an element. Might as well mention it now. The element is composed of individual atoms. And each atom has the identity of that element. Now you can subdivide that element down into smaller and smaller parts until you only have one atom. And that's as small as you can go. Now, when we represent elements, we use the symbol for that element. And that periodic table that I gave you with the red boxes around it also has some blue highlights in there. Those blue highlights represent elements that are commonly found in combination of more than one atom. So for instance, hydrogen, that is the symbol for hydrogen. But in nature, at room temperature and 1 atmosphere pressure, hydrogen will always be two atoms connected together. That's what we call diatomic elements. It may also be, it's the same way with nitrogen and oxygen and fluorine and chlorine and bromine and iodine. Oops. They're all diatomic elements. In other words, that's the way they exist in nature. But since they're only composed of the single atom, I mean, the atom for that element, they're still elements. Right? They have no other elements attached to them to give them a different character. This is the character of nitrogen. This is the character of fluorine, even though there are two fluorine atoms attached. Okay, those are elements. Okay, I mentioned the symbols. I talked about those. I don't need to hammer that one anymore. Those are the correct symbols, but in nature, this one would be O2. Krypton is a noble gas, so it's never diatomic. Right? Noble gases, inert gases, they don't react with anybody. You can force them, but typically, you just write the symbol and that's it. Okay, now where do these symbols come from? Well, most of them can be derived from, or rationalized from English. So oxygen is O. Aluminum is Al. H is hydrogen. But there's some elements that don't fit the mold, like iron. That's Fe. Right? It's not IR. And definitely it's not I, right? Because I would be iodine. Now, why is this one Fe and that one's not some other weird one? Well, it's sort of historical in nature. The derivation of this lettering system for the elements often depends not upon the English word or a word in some other language that is closely resembles English, but it may be derived from the Latin. And in this case, Fe stands for ferrum, which is Latin for iron. Okay? There are several examples. Let's see. Let me pick another one. How about K? K is potassium. Right? And in the Latin, it's Kalium. Okay? So the symbols follow the pattern, capital letter or a capital and small letter, but they don't always come from the English. They can't be associated with the English. There's several of them like that. And you'll encounter them. I mean, once you start learning the symbols, you'll find some that just don't match. And they're based upon the Latin. Well, I guess the Greek is possible too, because the Latin stole everything from the Greeks originally anyway. The Romans, that is. Right? And all the rich people had Greek tutors. So, when some lawyer or doctor starts to get high and mighty with me and starts saying we owe everything to learning Latin or the Romans, I say, okay, that's fine, but the Romans stole everything from the Greeks anyway. Right? And there are a lot of words that we use in the sciences that are derived from the Greek, not the Latin. Oh, here's a good one, gold. Gold is AU because aurum is Latin for gold. Lead is PV. It's not LE, it's PV because it's derived from the Latin plumbum, which I think is kind of funny because in Latin, plumbum means heavy. And lead's heavy. Okay. So here's a list of some common elements. You should have in the, well, if you have a hard copy book, usually in the front, under the front cover, they have the elements listed in alphabetical order like this with their symbols. And then maybe under the back cover, they have the periodic table. Or you can find a periodic table on the internet that has the symbols and the names together. It's just, I didn't build it that way for practical purposes. Plus, I don't want to make it that easy on you. You need to work, right? That's how we learn. We exercise this muscle. And believe it or not, the brain is like a muscle. In fact, if you don't use your muscles, they tend to atrophy, right? People that are bedridden, they have to be exercised artificially by their caregivers. Otherwise, their muscles just waste away to nothing. Well, your brain's the same way. If you don't use it, you lose it. And the stuff that you actually struggle with, that's the stuff you remember forever. That's just the way the pathways, the synapses and the pathways form in your brain. If you struggle with something, you will remember it. I can remember stuff I missed on tests back in high school. I never forgot them. Like, what's the Blitzkrieg? I missed that one on a test. I know what it is now. It was the German way of warfare in World War II. Okay, so let's look at, I don't know why I got Dalton's atomic theory up here. We're not going to look at Dalton yet. We're going to look at sort of in a chronological order the development of chemistry and those responsible for the modern world as we know it as chemists. The law of conservation of mass was developed by Antoine Lavoisier. He was a Frenchman. And if you know anything about history, 1773 was coming up to a tumultuous number of years, right? For in America, of course, we were getting ready to kick the British out. But right after that came the French Revolution. In the 1780s, I think, primarily. And Lavoisier was a brilliant, they called them natural philosophers in those days. They weren't called chemists or physicists, natural philosopher. But he did work on in chemistry and determined that during a chemical reaction, there is no creation or loss of mass. In other words, what you start with has its characteristics, the identities of the reactants, and then they react and they produce products. And all the product mass is exactly equal to the reactant mass. Okay? And that's his law of conservation of mass. Notice it's a law. It just says this is what happens. It doesn't explain why. That comes later. Okay? Matter is neither created nor destroyed. Let's see. Oops. I want to talk about Lavoisier again. Lavoisier, just never lose sight of the fact that all scientists are humans. Right? And they make mistakes. They may be brilliant in the sciences, but they may not be quite as astute in the social environment or political environment. Lavoisier, well, he saw an opportunity to make a few extra dollars. So he bought a contract from the crown, from the King of France, to collect taxes. Right? That's the way they did it in those days. You collected taxes from this certain geographic area, and you gave the king what he asked for, and you got to keep the rest. So everybody hated tax collectors, even then. Right? We hate them now. They hated them then. Only in those days, unfortunately, Lavoisier was still around when the French Revolution hit. And people like him who were tax collectors, they may not have fallen under the guillotine in normal circumstances where the rule of law was obeyed. But in those days, he had lots of enemies. And one in particular, whose name escapes me at the moment, saw to it that Lavoisier was thrown in prison, and then Dr. Guillotine's device did the rest. Right, so we lost that mind. Next, a little bit later, not too much later, was Joseph Proust, who was an Englishman. And he proposed and gave physical evidence for this fact that any compound, right? A compound is a combination of two or more elements bonded together in such a way that they produce a new identity. They don't have the same identity as the elements from which they're composed. For instance, when we react hydrogen and oxygen, what do we get? We can get water. Right? Hydrogen and oxygen are gases. Water at room temperature is not a gas. Right? There's one example of a change in identity. Plus, water doesn't react violently with other elements. Hydrogen is like a fuel. Oxygen is the oxidizer. And we use those two in some rocket engines because they can release a lot of energy. Very, very densely packed energy that can get a rocket into space. These are separate identities. But if what Proust was saying was that You identify your compound as pure and separate from any other element or compound. Right? Now you've determined that. What he's saying is that it doesn't matter where that compound came from, how you got it. Did it occur by a reaction of hydrogen and oxygen to make water? Or did you just take seawater and purify it? And now you have pure water. It doesn't matter the source. Once you've identified the compound, and it has those characteristics identified for that compound, you're sure that it's pure. In that case, wherever that compound came from, the ratio the composition of the compound, the ratio of the masses of the elements in that compound are always the same. So for water, 8 grams of oxygen will always be combined with 1 gram of hydrogen. That ratio is permanent and fixed for water. Right? For any other element, say the same thing. Just determine what the mass ratios are, and no matter where that compound comes from, it will always have that composition. That's the law of constant composition. Sometimes it's definite composition. You may see it that way also. Okay? Then comes John Dalton, just a few years later. See, we're progressing chronologically here. Science builds on itself over time. It doesn't just come full-blown out of somebody's head. The law of multiple proportions was proposed by John Dalton. So what do we mean by that? Well, he was an Englishman too. Multiple proportions just says if you have 2 elements that can form different compounds. For instance here, nitrogen and oxygen. In this case, we have 1 atom of nitrogen and 1 atom of oxygen. In this case, we have 2 atoms of oxygen. In this case, we have 3. What Dalton was saying, and he didn't, at this time, he didn't know that. We know this now. This is how it's written. But when Dalton proposed his law of multiple proportions, he was just saying that if you fix the mass of 1 element at a certain amount, and we know in the compound, the ratio, according to Proust, is going to be a fixed ratio, then if you have another compound that's formed from those same 2 elements, but it's a different compound, right? And you know it's a different compound because it has a different identity. Then that different compound will ratio the second element by whole numbers. So if you have a certain amount of this one, and you fix a certain mass of that one, then for this one, with the same mass, you'll have twice as much of the second element. And for this one, you'll have 3 times as much as the second element. That's multiple proportions. Okay, so now we're going to get into, I think we're headed into a theory here. Let me look ahead just a couple of slides. Yeah. Okay, so now we're going to get, up to now we've talked about laws, what we know about the chemical world in terms of just what happens. Now John Dalton is going to bring all that stuff together and say, this is why those laws work the way they do. That makes it a theory. So he needed some propositions, some postulates, if you will, that will define the limits of his theory. He said most natural materials are mixtures of pure substances. That's no great surprise, but it had to be said. Pure substances are either elements, right, that cannot be reduced any further by chemical means, or they're compounds. combinations of elements. And a given compound always contains the same proportion of massive elements. In this case, he was just restating the law of definite proportions that Proust proposed. Now, once we have those ideas in mind, Dalton said, this is why things happen the way they do. And for this first one, elements are made up of tiny particles called atoms. That's the simplest form of that element that still retains the properties of the element. Okay, he stole that one from the ancient Greeks. Well, he didn't really steal it. He took their idea and ran with it. The ancient Greeks said everything was composed of the atom. A few atoms, many more atoms, whatever it took. This is a Greek word that is composed of not. A is a prefix in front of any word, means not. It's just the opposite of what the root is. And the root, this root in Greek means cut, or divide, or split. So it's not cut. So an atom can't be cut any further. That's what they mean. So Dalton took that. What the Greeks said was that all matter was composed of the same atom. Right? The atom had a singular identity, and that's where they stumbled, because they couldn't use that basis, the atomic theory of their day in the ancient Greek. They couldn't make that fit the real world. So they had to come up with other things like the four elemental forces or substances like earth, wind, fire. What's the other one? Earth, wind, fire, water. There were four of them. But they had to go into all kinds of gyrations to make their atomic theory work, and it never worked. So Dalton took that and he said, okay, the Greeks were close. The problem was every element is composed of a different atom. Each atom for each element is different than the atoms from another element. So that's how we fix that problem. Right? And all the atoms of a given element are identical. This is Dalton's theory. Okay? They're identical within the element, but they're different than atoms from other elements. Okay. So then he said, the way different substances are formed is by different combinations of these elements. Right? You put atoms together in the form of a compound, you get a different substance. Right? So if we take one element and combine it with the other element, with the atoms of another element, we produce different compounds. So nitrogen and oxygen can produce nitrogen monoxide. It can produce NO2, nitrogen dioxide, or it can produce N2O, dinitrogen monoxide. Everybody knows this one if you've ever been to the dentist's office and needed some sedation. This is laughing gas. Okay. But they're different identities, different compositions, producing different results in a chemical reaction, but they're composed of the same two elements. So Dalton said, that's why the law of constant composition and the multiple proportions works. Okay, so he answered his own question in that previous law that he proposed, multiple proportions. Okay. Atoms cannot be divided any further by chemical means. That is true. It was true then, it's true now. Chemical means cannot break an atom any further. And the reason that Lavoisier's law of conservation of mass works is because the reactants have a certain number of atoms. And then when you rearrange them during the reaction, you get a certain number of atoms in the product, which are equal to the same atoms that were in the reactants. That's why matter is conserved, because you have the same atoms. You can't create or destroy atoms. So that's why Lavoisier's law works. Dalton fitted into his theory. It just rearranges, like you just, somebody blows a whistle and you swap partners in the dance. Okay. Now, this is the way science works. There's no such thing as settled science. Science is never settled. It is always open to questioning. Now, there are some things that are agreed upon and over time have been proven to be effective at solving problems, and we continue with those. But ultimately, everything is open for discussion, for debate. And when at times science has become stagnated because the prevailing understanding of nature has been stale. In other words, for instance, back in the beginning, in the 18th century, there was a theory called the phlogiston theory. And I won't go into its details, but eventually it was debunked. So it had to be thrown out. But for the longest time, scientists were boxed in by this theory and they couldn't think outside. So they were unable to solve some problems. It was only when John Dalton proposed this theory, and by experiment, it was proven to be effective at solving problems, that eventually the phlogiston theory it was gone. And unfortunately, as scientists age, they hang on to their pets. So sometimes the only way science advances is for one generation just to die out and let the new generation think new thoughts. So let's look at Dalton's theory in terms of whether the postulates of his theory are still true today. So that's what this question is. Which of these are true? Elements are made of tiny particles called atoms. Yep, that's still true. It was true then, it's true now. All atoms of a given element are identical. Nope, they're not. They have very similar chemical behavior. In that way, they're identical. But they're not all identical, and we know that now because we know about isotopes. Right? One atom compared to another atom of the same element, this atom might have an extra neutron in it. We'll talk about that in a minute. But this one is false. Okay, that one's true. A given compound always has the same relative numbers and types of atoms. That's true. It was true then, it's true now. And atoms are indestructible. Nope. Nuclear, sometimes they call it nuclear, that's nuclear physics. Atoms can be ripped apart. We can actually build unknown atoms using nuclear means. So these two are still true, those two are not true. Okay. So how do we write words in chemistry? Well, first of all, we need to understand another convention. When we write a chemical symbol, and I'm going to use this that's a generic chemical symbol. There's no X in the periodic table. There's an XE, but there's no X, so I get to use that one as a periodic symbol. there are 4 positions around that symbol that are reserved for certain information. If we put something up here, we're saying that's the charge on that atom. Right? Is it positive or negative? Or if we don't write anything up there, we're saying it's neutral. Or sometimes we say, okay, explicitly, I want you to know that that is a neutral atom. I'll put a 0 there. But if it's an ion, if we form a charged version of that atom, it may have a +1 charge. It may have a -1 charge, or it could have 2 minuses, or it could have 2 pluses. That's where the charge goes. Down here, you're saying, so this is the charge. Down here, you're saying numbers of atoms. So if in a compound, you write that atom, that element symbol in a compound, you say how many there are in that compound with a subscript. Now, if there's only one of them, you don't write anything. Because if you got the symbol, you got at least one. Otherwise, it wouldn't be there. Right? So we throw that out as redundant. Only if you have 2 or more do you write numbers of atoms there with an explicit number here. On this side, this is nuclear information. This one is Z, or the number of protons. Okay? This one is A, or the number of nucleons, we call it, which is equal to the number of protons plus the number of neutrons. Right, so those positions are reserved for that information. In chemistry, we don't always write these in here because very often they're not important. But if you see information in any of those 4 positions, you know what it's there for, what it means. Okay, I think I've got a slide about this, but I thought stream of consciousness, now's the time. Okay, so when we write a compound, we write the symbol for that element. And the symbol for the element in one avenue of thinking represents a single atom. So when we write water, we're saying 2 atoms of hydrogen are combined with 1 atom of oxygen to make a water molecule. And that's what we call a molecule. When you combine these atoms such a way that they behave as a single unit, that's a molecule. It's also called a chemical formula. It says, what are the elements in the formula? How many of them are there? Here we have 3 oxygens combined with 1 sulfur to make that compound. Okay, this just reiterates what I've said before. Okay, so here's a problem. The pesticide DDT. I don't know if you've ever heard of that one. It was widely used back in the 60s until it was discovered that some of the breakdown products of DDT in nature were wreaking havoc on wildlife, particularly birds, because it weakened their shells. So they'd lay their eggs and then they'd sit on them to roost and they'd crack them. And that was the end of that generation. So DDT was eventually banned. But that doesn't change the fact that DDT is a compound and we can write it. Right? If we know that DDT is composed of 14 carbons, okay, and 9 hydrogens and 5 chlorines, right? That's the molecular formula for DDT. Now, that doesn't tell you anything about its structure, but at this point, we're just talking about What's the formula? Okay. Now, we're going to get a little more history. I've already said that atoms are not indestructible, and the atom of one element is different than the atom of another element. Now we're going to find out why that is. Why is one element different than another element? Why does it behave differently than another element? We need to know something about the internal structure of the atom in order to answer that question. So, in the late 19th century, J.J. Thomson was a British chemist. By now, I think they call them chemists or physicists. And he discovered, actually first he postulated and then eventually proved that atoms were, at least in part, made up of a negatively charged particle he called the electron. So this negatively charged particle was part of an atom. And we use that symbol for the electron. He was working with the cathode ray tube, which was a new toy in those days. It was an evacuated tube with only a very, very, very small amount of some gas inside. And you could choose the gas, whatever you wanted it to be. And between two plates, there was a charge. Right? The electricity had been around for a few years, and you could make one charge positive, one charge negative. Let's make this one negative and that positive. And then you could see, once you applied a charge to those plates, you could see a beam going from the negative plate to the positive plate. So he knew that the particles were negative. They were going from negative to positive. And he could see the beam because there was a rarefied gas in there, very low pressure, not enough to actually quench all the electrons, but to show you their path. And they would go straight from one plate to the other, right? So he said, okay, I think these are negative particles, and their behavior, I'm convinced, is also negative. So on either side of that evacuated tube, he put more electrical plates, and he knew one was positive, one was negative. And when he did that, the beam bent toward the positive. Right? It was in an electric field, so the negative particles and the positive were attracted to it. So we knew they were negative. And he did the same thing with magnets and confirmed that the particle was negative. Right? And it was coming from atoms in those plates. He could make the plates out of anything he wanted to, and he'd still get those negative beams. So he knew it was something that was common to every atom, the electron. But the one thing he couldn't answer at this point was, if the electron was coming from the atom, what was balancing that charge? Right? He knew the charge was negative, but atoms are neutral. So there had to be something positive in there that was balancing the negative charge. And that was postulated to be the proton. Right? Here's a reconstruction of his cathode ray tube. And the first proposal was what was called the plum pudding model, accredited to William Thomson, who was also Lord Kelvin. But it's very likely that Thomson proposed it originally and Kelvin just picked it up and ran with it. But his proposal said that this is often called the plum pudding model because it was like these are the particles of plum and this is the pudding. And the pudding is positive and the plums are negative. So that would balance the charges. And that's why it was given that name. Now, before we leave the electron, Robert Millikan was a brilliant chemist in the United States. The ratio J.J. Thomson also determined the ratio of charge to mass. In other words, well, not in other words, that's all there is to it. The ratio of how much charge is on an electron relative to its mass. But what he didn't do was determine the mass of the electron. That was up to Robert Millikan, who performed experiments with a device that he built himself. It was an evacuated chamber with a sight glass in it, and he could watch little oil drops move up and down after they had acquired a charge. And to make a long story short, eventually he calculated the mass of an electron, and it was extremely small. So it had this charge on it, but it was almost no mass at all compared to the atom. Right? So it had the charge, but it had no mass, practically. Right? So a single electron has this charge, and these are standardized units. It's a very, very small charge, and even a smaller mass, like 10 to the minus 31st kilograms. It's very, very small. And for this, he got the Nobel Prize in 1923. In addition, he also looked at some of the work of Albert Einstein and the photoelectric effect. We haven't covered that yet. But his work on both the electron and confirming Einstein's photoelectric effect got him the Nobel Prize in 1923. Okay. Now that we know the mass of the electron and we know the mass of the atom, we knew that most of the mass of the atom was due to this positive, mystery positive charge. And Ernest Rutherford, who was an Englishman, proposed that the mass of the atom was confined to a very small, dense central part. He called it the nuclear atom. The nucleus of the atom was where the positive charge resided, where most of the mass of the atom resided. And the electrons were out here somewhere. Okay. So he needed an experiment to confirm that. And what he also needed was some way to investigate the atom itself. So he needed to fire a particle at it, see what happened. And the particle he chose was so this is a comparison of their models. Thomson's plum pudding model versus Rutherford's nuclear model. So with Thomson's model, if Rutherford fired, yeah, I'm about out of time. I'm going to have to keep going and just finish the recording. If you have to go, then okay, go. I'll post it later. He fired an alpha particle. It's a nuclear particle that had been discovered at the time, and it had a 2+ charge, but it was pretty heavy. And now we know it's actually the helium nucleus. But he fired this one. He needed something pretty heavy because if it struck the nucleus, it would have to carry some of its own momentum with it. And in Thomson's model, if these particles were fired at Thomson's plum pudding model, then they would all just go right straight through. So they go through and make a single beam here. So here's he used gold foil. He needed a very heavy atom, but it needed to be really thin. So he only had just a few atoms thick. Right? If you had too many atoms, it would just block the beam altogether. So we had it very thin, and here's your alpha particle source. And if the plum pudding model were true, then they'd all go through and end up over here at his detector. You can see him over here, a bright spot, that's it, nothing more. But if his model were true, and this alpha particle struck the nucleus where most of the mass resided, then you get some deflections. And that's exactly what he saw. So Rutherford put the plum pudding model to bed. It's no longer a viable theory. But the nuclear theory was carried the water from here on out. Okay. So the majority of the mass of the atom is now known to be in the nucleus. Positively charged nucleus, and the electrons are in this cloud or region outside the nucleus. So if it struck the nucleus, it would bounce off. Okay, enough of that. So here we have a summary of the development of how the atom is built. Dalton's atomic theory said it was a solid particle. I didn't know what was inside it. Then Thomson said that there were electrons. And in order to balance the charge, he had to create this model, the plum pudding model, to account for the positive charge. Well, Rutherford came along and said, no, it's a nuclear atom. Most of that positive charge is in a dense central nucleus, and the rest of the negative charges are outside here somewhere. Our modern concept takes this a step further and says that these electrons are not really particles. They're more like waves that occupy that space outside the atom. And now we know that it's not just that they're waves, but actually electrons behave as particles or they behave as waves. Right, so we're not going to beat that horse anymore. That's just chronological development of the structure of the atom. Okay, so, and this is another graphic. It sort of shows the progression. We stuck Niels Bohr in here, but we're not going to spend time here. Erwin Schrödinger produced the wave model. Okay, now there's one other problem. Atoms, while most of the mass can be attributed to the proton, it's not all of the mass. They knew by now that there was more mass in the atom beyond that balancing charge. Positive, negative. There was more mass in there, in the nucleus. So they knew it had to be neutral. It couldn't be charged because then you'd have an imbalance again. So Rutherford had a graduate student, and later I think he became a research assistant, Chadwick by his name. And Rutherford had Chadwick work on this problem and say, all right, we need to identify this other particle that's neutral. So Chadwick did. And he eventually proved that there was another particle in there called the neutron, which was about the same mass as a proton, but had no charge. So now they've accounted for all the mass in an atom. Electrons, protons, neutrons. That's how we build an atom, with those three particles. Okay. Now, by comparison, if we say the electron weighs 1 unit of mass, the proton is about 1,800 times as big, and the neutron is just a hair bigger than that, by comparison. Okay, so most of the mass is attributed to the proton and the neutron. So, now that we know that the atoms of different elements are different, and how they're different, what is it about that gives them different chemistries? Why do they react differently? Well, think about it. If the nuclear atom has a very small, dense nucleus here, and then the electrons are out here, when two atoms come together, what do they see? They see electrons. So the electrons, that's where the chemistry happens. So we need to know more about the electrons. and how they behave in a reaction to determine, to even quantify the chemical behavior of one element versus another. Okay, so it's the number and the energies of these electrons that determine their chemical behavior. And we'll talk more about that in a little bit. But for isotopes, remember that neutron part? The identity of any element is due, let's see, hydrogen, helium, lithium, for instance. Remember what I said? What is in this position here? The number of protons. So this one has 1 proton, this one has 2, this one has 3. The number of protons in the atoms of an element determines the nature of that element. So if you have a different number of protons, you got a different element. And that's why they're arranged the way they are on the periodic table. One of the reasons, from upper left to lower right, you increase the numbers of protons. Right? We see hydrogen here, then we go helium, then lithium. Beryllium has 4 protons, boron has 5, carbon has 6, nitrogen has 7, oxygen has 8, fluorine has 9, neon has 10. You keep adding protons and electrons to go along with them because the atom's neutral. Then you get a different element each time you add a proton. But as you add the protons, you can add neutrons too. So helium typically has 2 protons and 2 neutrons. So 2 plus 2 is 4. So that number is going to be 4 because it's the total of protons and neutrons. If we have, let's use carbon. 6 protons make carbon. But carbon can either be 12, which means 6 neutrons, or carbon can be 13, which means 7 neutrons, or it can be 14, which means 8 neutrons. Those are isotopes of carbon. They're all carbon. They have the same number of protons, same number of electrons, but different neutrons. So they have different masses, but they have similar, almost identical chemical behavior. In fact, the chemical behavior is so much alike for each isotope, you can't separate them by chemical means. Okay. And every naturally occurring element, all the elements in nature, are mixtures of isotopes. There are no pure single isotope elements in the universe. They're all mixtures. So you have at least 2 isotopes of every element, and some have many, many more. Sodium, here's an example. In this one, 11 protons mean sodium. 11 protons mean sodium. 12 neutrons means this isotope, and 13 neutrons means that isotope. Okay? Let me see how much further I have to go. A little ways. Okay. So what more do we need to know? All right, here's the simple thing. This only has the, this is called the atomic number, the Z number, and A is the mass number. The mass number is simply the sum of protons and neutrons. So it's always going to be a whole number. Okay, so I showed this one earlier. That's carbon-14. It always has 6 protons but it can have different numbers of neutrons. Notice also that when you form the charge on a carbon, if we say we remove an electron, if you take away an electron, now you have only 5 electrons and 6 protons, which means what? You have a +1 charge. There's an imbalance. Or if you add an electron, now you have 7 electrons. So the charge on an ion is based upon the balance of protons and electrons. And one thing you never do to make an ion out of an element is change the number of protons. But what happens if you do? You get a different element. So the charge is always based upon the balance between the protons and electrons by changing the number of electrons only. Okay. So if we have an isotope that contains 23 protons and 28 neutrons, what's the mass number of that isotope? 23 plus 28? 51? 51. What's the identity of the element? Well, to do that, all you need is a periodic table. Right? Rather than use the one on the wall, I use this one. So we're looking for 23 protons. That's the atomic number. Right? So we go along here. It gets bigger from top to bottom and left to right. So we just keep following along until we find 23. So we go along here, 23. And 23, you can usually identify the atomic number in a periodic table if it's different than this one. You look for the one that's increments from left to right and top to bottom by ones each time, right? Whole numbers. So if we follow and look at 23, we find it's vanadium. Right? So vanadium, or V, is the symbol for this element. Now, how about the periodic table? What are its origins? Well, the periodic table, like I said before, is one of those things that just didn't explode full blown out of somebody's head. It came from developments. And let's see, maybe in this course, we're not going to go into as much detail. But there were other scientists who were noticing chemical and physical trends with different elements. And they noticed that these elements are grouped together because they behave similarly. They're not exactly alike, like all the halogens, right? Fluorine, chlorine, bromine, iodine, they're all halogens, and they behave similarly. Not identical, similar. They're in a family, a group. The alkali metals, the far left side of our current periodic table, those are lithium, sodium, potassium, rubidium. They all behave similarly too. And scientists were noticing this. But most of them, in fact, all of them, up to this point, didn't make the jump to prediction. They weren't able to say, there should be an element in here, in that family, that's missing. We haven't discovered it yet. That's what Mendeleev did. He put these things together by primarily their physical and chemical behavior in the families. And his original periodic table, this is all in Russian, because he was Russian. His original one grouped them from left to right. But notice, periodically, he would say there should be an element in here with that mass. And there should be an element, let's see, where's another one? There's another one here. That was sort of a question. But there should be elements in these positions with these characteristics and this mass. And that's how he built his periodic table in such a way. Now, this is later. He took his groups now and made them vertical. There are missing places in here where there should be elements, and they're going to have these characteristics. And what he noticed was the reason he did that was you move along, the elements get heavier and heavier and heavier as you go down the periodic table. And if you put them in order of the known elements, some of the elements lined up with the wrong groups. They didn't have the same physical and chemical characteristics of the other members of that group. So he said, it doesn't go there. We're going to slide it over here because it's more like these. And this is going to be an empty hole until somebody comes up and discovers this missing element. It will have these characteristics. And he was right every time. That's why Mendeleev is given credit for the periodic table, because he used it to predict the discovery of unknown elements. Okay, this is our current periodic table, or one version of it. And you'll notice here, these are the atomic numbers. They get bigger, one by one by one, from left to right, and then you go down to the end, and you start over again. That's known as a period. When you go this way, you go back and start over again. In physics, the period is usually referred to in terms of periodic motion, like for a swinging pendulum. The pendulum's moving, yeah, but it moves to one place, it goes back, it goes through a cycle and comes back to the same place. That's one period of motion. The periodic table is like that. You go down here, these elements are like the ones in the family in a group above them, but when you get down here, if you go to the next one, 55, there's nothing out here, right? But if you go back over here, it turns out this one behaves like those guys. So we go through a period and then we double back because this one is more like those. So that's what the period is, from left to right. And the groups are vertical because they have similar chemical and physical characteristics. Okay, that's known as the periodic law. We go down to the end and double back because the swapping, returning to the beginning in that period, in a new period, allows you to place elements in the proper groups based on their behaviors. Now, the atomic number, we didn't know originally that the atomic number that we identify now with the number of protons, we didn't know that until Henry Moseley, who was a young chemist, did the experiments. And in fact, his experiments were not based upon numbers of protons. He didn't use that approach. He used X-ray crystallography. And he had a formula, and he noticed that going from one element to the next, he could predict the wavelength of the X-ray that was absorbed by that compound, the element. And all he needed was one whole number in that formula. Change the whole number, go from here, make it 23, and that X-ray absorbance would occur for that element. Now, unfortunately, Henry Moseley, notice he did that work in 1914. Well, he finished that work, and then he went off to World War I and got killed. So that was the end of that brilliant career. Okay, so now we go to the structure of the periodic table. The way it's built now, we can say there are metallic character elements and there are non-metallic character elements. And there are certain things that are common to the metals, like luster, like malleability and ductility, conduction of electrical charge through the material, conduction of heat is good. All of those are characteristic of metals. Non-metals are just the opposite. Non-metals don't conduct heat. They don't conduct electricity. They're not malleable, they're brittle. Actually, the solids are brittle. Most metals, all but one, at room temperature is a solid. Mercury is a liquid. The non-metals could be gases, liquids, or solids, any one of those. And the way we divide them up, let's see, here we go. So here we have our dividing line, here, this black line. And when if you want to attempt that periodic table, extra credit, you'll know that you need to put the black line right here. All right? I have students who will attempt that thing, and they'll get it wrong. They'll go down here and then go like that. And it's just simply looking at a periodic table that's set up this way, or going back to this slide and saying, there's the blank line. Put it on your table. Okay? Don't just do a hatchet job on it. Try to learn something. Okay, so that's the division. Metals are on this side. Non-metals are over here. So most of the elements of the periodic table are metals. Now we have a few right along close to this black line that under certain circumstances exhibit metallic behavior. And under other circumstances exhibit non-metallic behavior. Those are called metalloids. And the ones that are metalloids can vary depending on the author. But in general, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine are all metalloids. So we use this behavior in our semiconductor industry, right? All your electronic devices are based upon this metalloid behavior with silicon as the base. Okay. Here's another table that divides metals, non-metals, metalloids, noble gases. Some of the groups have special names. Let me see. Are we going to get those? No. Okay, let's go back. Come on. Go backwards. Go backwards. There we go. Oh, we are going to get to those eventually. All right, so we can move on. Sorry. Most elements if the element is pure, will be very reactive. In other words, they don't want to be pure. Most elements in the universe, in the Earth's crust, wherever you look, are going to be combined with other elements. They're going to be in compounds. There are a few that are relatively non-reactive, like gold, platinum. The noble gases are non-reactive, so you'll find them in pure form more readily than others. Right. The noble metals, silver is kind of borderline. You can find pure silver, but very often silver is combined with something else. But gold and platinum are usually found uncombined in nature. Noble gases, these are the diatomic elements, and I've identified those in this sample periodic table right here with the blue background. All of those are diatomic. Now, why should I want to emphasize that fact? Because if you're given a word problem and you have to write a reaction, and it says oxygen reacts with potassium, you could write K as a reactant and oxygen as a reactant, whatever it produces. And this is wrong because oxygen is diatomic. It will react like this. And you need to know that because the word problem doesn't tell you. Okay, what's an allotrope? An allotrope is a pure element, but it's a different form of the pure element. And for instance, the diatomic elements are allotropes of that element, and some of them occur in different combinations, not just diatomic, depending on the circumstances. Carbon's a better example. It's not diatomic normally, but it can occur in different forms. Right? Diamond is a form of carbon. It's a network solid. Graphite is a form of carbon. This is a weird one. Buckminster fullerene. It's a combination of carbon atoms, 60 of them exactly, that forms kind of a ball. So they call these buckyballs. And then nanotubes. You can form carbon nanotubes. And the exercise garment industry is taking advantage of carbon nanotubes because they have certain characteristics that are, lend themselves to breathability and an absorption of odors and perspiration and so forth. So they're advantageous. There are physical reasons for using nanotubes. It turns out that they're good conductors of electricity in the proper form, but they're all carbon. There's only carbon in these and nothing else. Let's see. There's a nanotube. Okay. I mentioned how we form ions. And I'll just say briefly that when you form an ion, you change the number of electrons only, never the number of protons. If you change the number of protons, you have a different element. So you change the number of electrons, that changes the charge balance. More electrons makes it negative, fewer electrons makes it positive. Okay? It's always the balance between the number of electrons and the number of protons. So if you only have 10 electrons in this ion, but there are 12 protons in the magnesium atom, you have a +2 imbalance, which makes the ion +2 charge. Okay. Let's see, here's another example. Oh, okay. Let's see. When you have a positive ion, any positive ion is a cation. And any negative ion, and this could be anything, it could be 2 + 3 + 4 + 2 - 3 - 4 - whatever, is an anion. So when I use that reference, when I say cation, I mean a positively charged ion. Let's see. Okay, I mentioned this earlier. Now we have different families or groups of elements in the periodic table, and they're in the vertical. That's a group. On the periodic table is the vertical. Some of them have names. The first one, the first group, farthest to the left, right here, are called alkali metals. These alkali metals, whenever they form ions, they always form with a 1+ charge. Right? They're the first group, 1+. Okay. The second group, they're called alkaline earth metals. They always form a 2+ charge. So the first group is 1+ charge, second group is 2+ charge. Now that's when they form ions. Right? If they're pure elements, then they'll be neutral, of course. But when they react and form ions, they form 1+, 2+. On the other end, we can forget the noble gases because they don't charge, right, normally. Then right next to them, to the left of the noble gases are the halogens, right? And before LEDs, the best technology we had for headlights in automobiles was the halogen bulb. Produced a very bright light, and it was predominantly the halogen in that bulb was iodine. But these halogens have similar characteristics, and whenever they form charges, we assign a -1 charge to them. Okay? So we've got the alkaline metals, the alkaline earths, and these are given to you as ions, just to emphasize that point. And then on this side, we have no charges here. We have a -1 charge for the halogens. Right? The next group over from the halogens are the oxygen group. We call those chalcogens. And they form a 2- charge. The next one to the left of oxygen are the nitrogen group. We call those pnictogens. Okay? And then this group doesn't have a name, but it starts with boron as a 3+, then aluminum's 3+, gallium 3+, indium 3+. That group is like this one, +1, +2, and then you skip the transitions and go up here, +3. Now later on, when we start talking about how these ions, how the electrons actually behave in an atom, you'll see that this is logical. And these transition elements, we leave those out for now. We'll talk about them later. But knowing the charges that can form from these atoms when they react is important to know when you're trying to deduce a chemical reaction. Okay, let's solve this problem. I mean, I'm half hour over, so if you have to go, then that's okay. An ion with a 3+ charge. So this ion has a 3+ charge, and it also has 23 electrons. Okay. How did it get a 3+ charge if it has 23 electrons? Right? It has to have 3 more protons than it does electrons. So if it has 23 electrons, but it needs 3 more protons to make it 3+, that means it has 26 protons, right? Add these together. 26 minus 23 is 3+, right? So now that we know the number of protons, we can identify the ion. Look up your periodic table, look for 26. Let's see. 26 is iron. So the X should be Fe, 3+. Okay? That's how we deduce the identity of that ion. We look for how many protons it has. That is definitive. If you know the number of protons, you know the element. How about this one? Okay. A certain ion, X+. What does that say? It's only got 1+ charge. It has 54 electrons and 78 neutrons. What's the question? What's the mass number of this ion? Well, you need to know the number of protons, don't you? If it has a 1+ charge, that means it needs 1 more proton than electrons. So it needs 55 protons, because 55 minus 54 is 1+. Okay. So now the mass number is 55 plus 78, which is 3, that's 133, right? 13, 1 plus 3. Yeah. So that's the mass number. Okay? Since we're here, what element is that? 55 protons? Let's see. 55 is cesium, CS. So this would be like that. Okay. What if your compound is composed of ions? Like sodium chloride. We've got a sodium ion and a chlorine ion. Well, the sodium is an alkali metal, so it has a +1 charge. Chlorine is a halogen, so it has a -1 charge. So only need 1 and 1, positive and negative. They balance the charges. That's why we write sodium chloride this way. Because this one is a +1, that's a -1, and that balances the charge. These ionic compounds typically have very high melting points. The bond between them is extremely strong. So it takes a lot of heat to turn that solid into a liquid. It can be done. They conduct electricity only if they're melted. Right? In the solid form, what are these ions doing? They're locked in place. They can't move, so they won't conduct electricity. Solid sodium chloride is an insulator. Right? In order to get a current to move in a conductor, you need something to carry the charge. In a copper wire, it's the electrons. They move the charge. In an ionic compound, the ions carry the charge between electrodes. But that only happens when they can move. And if they're solid, they can't move. So we have to melt them or put them in solution. Free up the ions so they can move. All right. So whenever we write an ionic compound, the charges have to balance. So let's say we form a compound instead of with sodium, we use calcium. So if you look on your periodic table, you'll find calcium in the alkaline earths, which means it has a +2 charge. So if calcium has a +2 charge, chlorine has a -1, how are we going to balance that charge? We need 2 of those, don't we? So 2 times a -1 is -2, and 1 times a 2+ is a +2. That balances. Okay. Yeah, they use magnesium in this one. Same family. Okay. Let's see. How am I doing on topics? Oh, just about done. So if we have this compound, it contains an unknown ion X with chlorine, XCl2. In that case, we know that since chlorine is a -1 charge, -2 total, and there's only 1 of these, that means this one has to be a 2+ charge, doesn't it? To balance. So we know the unknown has a 2+ charge. We're also told that this ion contains 20 electrons. So with this one, 20 electrons and a 2+ charge, that means we need 22 protons. That gives it a 2+ charge. Aha, now we know how many protons we can find out from our periodic table. Let's see, 22 is titanium. So now we know that's our compound. But, of course, if we write titanium as its ion, it's like that. And that was the question. It helps to go back and read the question sometimes. So X is titanium with a 2+ charge. How about this one? A member of the alkaline earth metal family. So we know that's in the second column from the left. most stable ion contains 36 electrons. That's 36 electrons, and it forms a compound with bromine. What's the correct formula for this compound? Well, we know that if this is an alkaline earth, it has a 2+ charge. So it's going to be this. Right? That means bromine, if there's only one of them, then we have to make that assumption. There's going to be 2 bromines because it's a -1 charge. Now, what is X? Well, if it's 36 electrons and it's a 2+ charge, we need 38 protons. And 38 protons means strontium, Sr. There we go. So it should be D. Okay? And we're done. So, the moral of this story is learn those elements, element symbols. Otherwise, you won't be able to do any of that stuff. Not easily, anyway.